Hi, and this is the PhysicsHigh podcast. A quick quiz. Do you A, want to be inspired by science communicators? B, want to learn all about science education? C, want guidance on your scientific journey? Well, how about D, all of the above? So let's say you want to write books, maybe on science. So what topics would you choose? Maybe nuclear physics, quantum mechanics, maybe general relativity, hey, maybe even Bayesian probability. Now, what would your audience be? Now, you'd probably think maybe undergrad students, first year, second year, third year, or beyond. But babies? Well, today my guest has done just that. And not only those topics, but even topics such as chemistry and evolutionary biology. Chris Ferrie is an academic researcher based at the University of Technology in Sydney. Now, and originally from Canada, he is particularly interested in quantum informational science. But in his spare time, as well as raising a family, he's loving writing books to young kids and babies, hoping to raise their interest in science by introducing those topics at a very early age. Now, to find out why he does that and much, much more, let's welcome Chris. G'day, Chris.
Thanks for having me, Paul.
So, Chris, tell us a little bit about what you do before we start talking about your books for babies, which is what you're particularly well known for. But let's get to know a little bit about what do you do at the University of Technology?
Well, I'm an associate professor there, and that means that I teach and I do research and I do a little bit of service to the university and to the discipline itself. So I'm what's known as a balanced academic.
A balanced academic, yeah. Very good.
Yeah. It's a balancing act, that's for sure. So I lecture, this term, for example, I'm lecturing about Introduction to Quantum Computing, and I train graduate students. So I have students that are looking to obtain a PhD in engineering or science or physics, and then I do I do research with them, and then I have collaborators that I do research with, and then those are international collaborators all over the world.
Now, I think many of my listeners, particularly if they're high school students and beyond, probably know a little bit about what quantum mechanics involves, in particular in terms of the wave nature of particles and the standard model and so forth. There's lots of parts to quantum mechanics, but I'm not sure not many of my listeners would maybe understand what quantum informational science is all about. Could you give us a simplified version on what that entails?
Yeah, I mean, there's two different ways to come at it. If you're a student of physics and you know a little bit about quantum mechanics already, then you can come at it from that approach. And from that approach, the question is, can we build devices that do computation that are based on the rules of quantum physics instead of our conventional or classical physics? So the devices that we use today, including the one we're using right now to have this conversation, is based basically on Newtonian physics and a little bit of electromagnetism. Whereas quantum mechanics is different, right? And general relativity is also one of the modern theories of physics. But you could ask, can you build a computing device based on those rules? And if you could, what might it be able to do, right? So that's kind of the general, big picture questions. Now, it turns out in the 90s, it was discovered that if you could build such a device, you could solve some problems much faster than you could with a digital computer. And that's kind of when people became really interested and then there was lots of funding available to do it. The other way to think about it is just, if you just think, someone like Alan Turing would have thought, what is computation? Computation is a set of objects and rules that they follow. And I can just calculate things according to the rules. And you can dream up all sorts of things. In mathematics, you just come up with all sorts of things that they don't have to be real in the world. Mathematics can be very abstract, and ask, okay, well, what could I compute using these objects and these rules? And if I can do something interesting with them, wouldn't it be great if I could build something in the real world that could do those calculations automatically for me, right? So that's a way to think about, that may be a way that Alan Turing thought about computers, was he had these problems he wanted to solve. he could do the calculations himself, but wouldn't it be great if I could just build a machine to do it for me, and much faster and more reliable? Now we have these rules of quantum physics. Turns out we might want to solve problems using these calculations. People like me or other scientists, or really anyone who wants to do it, can do these calculations. But wouldn't it be great if we could build a device to do it for us automatically and without error?
Could you give us a little bit of an example, maybe one or two examples of the possibilities? Like what's a possible outcome or future technology that would be a benefit to us but uses quantum computational science?
Yeah, so the original thought for a use of a quantum computer was to simulate molecules, for example. So it's very difficult to simulate quantum systems like atoms and molecules, and certainly complex molecular interactions. And the thought was, well, if we built a computer that was just, inherently quantum mechanical, it was built of molecules and we could control the molecules themselves, then it would be very easy to simulate the interactions between them. So yeah, think about like an airplane. You wouldn't build an airplane unless you simulated that it would work first, right? And it used to be that you would do that in the real world in like a wind tunnel, and you'd put the model in the wind tunnel. But now it's all done on computers. Buildings, bridges, you wouldn't build any of these things unless it was first simulated on a quantum computer or on a computer. So now the question is, could we do the same thing for molecules? And molecules are important. Molecules are what you need to understand how to make new medicines, how to make new materials. And if we could simulate the interactions of complex molecules or the properties of molecules, then we could build new materials. Something that we might be able to build would be a superconducting material that works at standard temperatures, and then we could distribute power all over the world for free. I think the potential is really great for these devices if we can build them.
Coming to our next aspect of your career, you've published already, I counted 56 books that are catering really for young kids and babies, a number of babies in the title, and you've got quite a number in the works as well. Can you give us a little bit of history of what led to you starting to write those books?
Well, I wouldn't have written children's books had I not had children of my own. It's just one of those things. Like comedians who talk about like kids and family when you're young, you're like, this isn't funny, I don't get it. And then you have kids and you're like, oh, wow, there's a whole new world, a parenting world. So I never would even noticed children's books until I had kids. And then I started reading them and reading a lot of them. You read several a night, and then I have 4 kids now. And so it's reading a lot of them over and over. And I noticed that there wasn't a lot of science books. And I had very young kids at the time. So certainly there's lots of science books for kids, but they're not available for very young kids, and certainly not available for like first reading books. And so I thought, well, maybe I could write my own and I could just read it to my kids like I read other books. And so I got started, and I was struggling to think about, what I would write about. And then I thought, well, I'll just write about my research. Why not? It's a way to explain my research to my kids and, explain to them what I'm doing all day at the university and why I'm so excited about it. So I wrote Quantum Physics for Babies, and I just had my own copy that I had printed, a unique single copy, and read it to my children. And then I gave it to my daughter's classroom when she was in preschool, and they loved it, and they're like, oh, you should make more of these. And so I posted it online, and yeah, it kind of just grew from there. There's lots of excitement, so I wrote more books, and now it's just a life of its own, really.
Now there's more than just teaching your kids about these concepts, right? It's also about your value you place on introducing students at a young age to scientific concepts. You're sort of feeling like there's a gap that needs to be filled there. Is that the case?
I don't think like educationally, I don't really want to focus so much on like education, because then you get trapped in this like argument about like, how early should you introduce kids to certain ideas so that they don't fall behind. And I don't want it to be something where, university education or like preparing for university starts in the womb or anything like that. So mostly I think that the books are for parents. And so the reason is that when I speak to parents of my children's friends, you meet them at the park or you meet them in the schoolyard, and you tell them that you studied math or you're a physicist, you get funny looks. And the most common response is, I hated math in school, which I find really, really sad and depressing. And if I wanted to, I could feel a bit offended by it, right? To say, here's what I love, and then have someone say, I hate that is a bit weird. But it's encouraged in society, and it's certainly encouraged amongst young girls as soon as they show any sort of difficulty to say, well, maybe this isn't for you. Maybe you're not a math person. Why don't you do this other thing that's more traditionally suited to your gender or something like that. And so I found that having these really simple books gives parents and adults the ability to, reintroduce themselves to these ideas and start to enjoy them. And it seems to be in a way that makes them comfortable, right? That it's not, although it does say for babies, to them it doesn't feel condescending. They say, oh, this is at my level. And then they can read it with their children. Because I think a lot of scientific communication is pitched at such a high level. And unfortunately, a lot of scientific communicators are catering to this audience of people that really want to feel like they're intellectuals. And so the more big words you use, the more impressed they'll be, right? So I don't want to have like a new educational program start changing the national curriculum so that quantum physics is taught in kindergarten. I just think that, there should be a variety of options available, and there's not enough science options. And I think it's definitely needed, and people crave it because they want to like science. It's not that they want to feel like they hate math or they're bad at math. They just don't have a comfortable pathway in.
I find that really interesting, actually, that that you aren't doing this for the kids, but by subterfuge, you're actually educating the parents and exposing them to scientific concepts. And I guess those parents could be the same parents you talked about who were told, oh, you're not good enough for science or whatever. And now they're being reawakened to those interests in science, that they may think, oh, this is an interesting topic. I might look at this further just for interest's sake. So it brings up a really positive view of science, and yet, it's done in such a light-hearted way. That's fantastic. So clearly science communication is important to you. How do you see your role as a science communicator? We've talked a little bit about your books, but I assume there's other areas. I've noticed that you've also produced some videos as well. You're trying to communicate science, obviously, in different ways. How do you see your role as a science communicator in today's world?
Well, I will tell whoever wants to listen about science, physics, and mathematics. I've tried lots of different media, and I guess books seem to be working well for me, but I don't want to stop there because not everyone's a parent, or not everyone has young kids, but lots of people still want to hear and learn about these topics. I think the reason that I continue to do it, because there are many great scientific communicators, many much better than I am at it, but I think I have a unique perspective because, abstract mathematics and quantum physics aren't something that's usually talked about in public. Usually it's like, check out this picture of a galaxy or solar system and you're all connected to the cosmos and made of stardust. And that's all great. But it's really disconnected from what scientists really do. And especially theoretical physics, which is what these things are talking about. We're talking about, abstract ideas, not galaxies. When someone says, I look all day at a galaxy because I'm an astronomer, they're looking at numbers, right? And symbols and, voltages on spectrometers. And they're not looking at pictures of galaxies, not ones that artists have drawn. I do see this as a problem because as a university lecturer, I see the disappointment in some students who come in their first year and they say, I love physics. I read Neil deGrasse Tyson's book, which is a great book, especially if you listen to and read it in audiobook form. And they're so passionate and excited about it. And then you say, well, all physics is, at least at university, is I'm going to test you on mathematical problems, right? Because that's what you're going to do as a practicing physicist. And they become a little bit disappointed and disillusioned with it. So I'm hoping that I can, at least help paint a more accurate picture of what scientists, in particular, my kind of scientists, actually do.
So now back to you personally, Chris. What got you into science? I know you did a mathematics degree initially, but let's go back a bit further. You obviously had a passion for science at an earlier age because that's the path that you chose. Was it a seminal moment or was it just a gradual thing that you've enjoyed?
I think it's just a passive thing. My father in particular, he subscribed to things like, Scientific American and other popular science magazines, and was an avid reader of science fiction and like science fiction movies. So like science was always a thing that was around. So I was always aware of it, but I really enjoyed mathematics. And that was simply because I could never reconcile the fact in many of my other subjects in school that you couldn't get a perfect grade. So there was like this English teacher, I remember saying, the highest grade that I will give is 90. Whereas in math, if you get everything right, you get 100% and there's no ambiguity and everything's right with the world. So I was like, that's the kind of certainty that I want. There's enough uncertainty in the world. Let's, make as many things certain as possible. And so I focused on math and I had a really great year 12 physics teacher. And it was at that point where I started to think, when I go to university, I'll do math, but maybe I'll also like take electives in physics. And that's what I did. I did a math degree and all the free choices that I had were in physics. And I think that was put me at somewhat of an advantage because again, what happens in a physics course or a science course more generally is they want to convey concepts and intuition. The lecturer is in front of you, and he or she's trying to say, here's what I think about it, and here's how things conceptually happen in my mind, but on the test, I'm going to give you all these math problems. So I was able to do well in my physics courses because you're only tested on math problems because you don't have time to like give an oral exam to 300 students to find out what their intuition is like. So it was kind of like at year 12, I had this physics teacher that really kind of showed me that all of this math that you're learning, not only is it nice because it's cool and there's lots of interesting puzzles and things just for its own sake, but you can actually apply it to something and solve real world problems. And that kind of got me hooked, at least on that idea that I didn't want to just be a mathematician that just thinks about abstract math problems without any bearing on reality. I wanted to be able to use math to solve problems.
And then that moved into your PhD. What was your topic?
Yeah, so my PhD was in quantum computing, which wasn't taught at the undergraduate level. It's only starting to be taught at the undergraduate level in universities. So I met a researcher, and I was talking to them about the research that they did. They were one of my lecturers, giving a standard lecture in some topic in physics. And they said, I work in quantum computing, and you can be an intern in the summer in my lab. And so I did that, and I really enjoyed it. And so then that's how I moved into my PhD research, which was, kind of, started and kindled as an undergraduate intern.
So I assume there's a lot of maths in that.
Yeah. I mean, there is, but I don't think that anyone is incapable of doing it. So if you showed me the maths that I do today, when I started my PhD, I would just run away screaming. I would say, no, I can't, there's no way I can do that. But you do it every day for 8 hours a day, for 10 years, and you become good at it, just like anything else. And, if you, it's not even like, it's not as difficult as being good at sports or the cello or even being a mechanic, where it's grueling work. Math isn't like that. It's fun. It's enjoyable. And if you can find the right path, then anybody can do it. And I find that most people, they just fell off the path, and there's no mechanism to get people back on track. They fall behind, and everything that they hear is 2 steps ahead of them, and they just never catch up. Whereas if you're at the right level, if you're being taught at your level, then I think anybody can do it.
Now, you mentioned they fall off the path, but there's no mechanism to get them up. Is that something that you don't have an answer for? Or is it something that you have some ideas as to what we could address that? Because obviously we want to get them back on the path. People fall off the path all the time, but we want them to get back up again.
Yeah, it's difficult. I mean, I know how to do it, but it takes a lot of time. So with students that aren't up to speed on a certain technique in mathematics, then, we sit for hours a day at the whiteboard working through problems and building them up to that point. And of course, if you have a classroom of 30 people, you can't do that one-on-one with everyone, right? So yeah, it's a big challenge. I don't have, I know one way to do it, but I don't know a scalable way to do it. And it's interesting you mentioned earlier about scientific communication and the importance of communicating science to the public, especially in today's age where we have these many problems with anti-science and misinformation. Is apparently the answer, as far as the research suggests, is that you have to do the same thing. It takes a long time to undo some sort of miseducation, whether it's, if people get down the wrong path onto conspiracy theories, or if they just fall behind and never progress in their studies. It takes a long time.
But what you say, the solution in one sense is you just do what you can. For example, yes, you have 30 students, but if you can work with one student and get them, that's a success. An old illustrative story, and probably you have heard it, but it's, the old starfish, the thousands of starfish on the sand, and a kid's throwing them into the ocean one at a time, and someone says, "What are you doing? This is an impossible task. It doesn't matter." And he says, "Well, it matters to this one." That's what we do as teachers. We can't do everything for everyone, but we can certainly do with the kids who we've got in front of us, and if we've got time to do that individually. So that's a nice segue, really, in terms of what I guess the next question is we've got a student who's in high school and is considering maybe thinking about dropping science or deciding to continue with science. I'm leaving it open to you. What advice would you give them?
Well, I think that if they feel like science is something that they're interested in, that they're passionate about, then definitely stick with it. One shouldn't look for something that has no challenge, because you will find that you'll become very bored in life if you have no challenge. So the general piece of advice, if you have choices as a student, is to learn as much math as possible, because math is applicable whether you stay in science or whether you decide you're going to go into finance or whatever it might be, right? You want to be an accountant, it doesn't matter, right? Or just generally, make it through life. Mathematical thinking is a very powerful tool that you can apply to nearly everything. So the general piece of advice that I think will work for everyone is practice and study math. Depending on what sort of science that you want to get into, then you can get into more tailored pieces of advice. But another piece of advice that I like to give people is that universities are public spaces, and you can walk into the science building and find an open office door and knock on the door and say, hey, I'm Chris, I'm a high school student. I wanted to hear about your research. And every single academic researcher will spend the rest of their day talking about their own research to whoever wants to listen. So if you want to know what science is like, then just start sending emails to people at your local university, and you'll find that you can get started on getting a taste of what real science is like today. So I've had high school students come in over the summer, communicated with them online to give them kind of little projects to do and give them a sense of what kind of research that we do. And I'm happy to do it. And the more people that hear about our research, the better.
My last question, a lot lighthearted. I'm giving you an opportunity to share something, and I think we might be sharing a little bit of your bookwork.
Sure. Yeah.
Tell us, what are you going to do?
That we should definitely have a read. So as you mentioned, there's quite a few books now, so I had to choose. So this one actually is my favorite. Now it's going to look a bit weird since I have a green screen, so the green's not going to show up. But I have a solution to that, so I can show you the electronic copy. I can share my screen and show the electronic copy as well. But I do want to show you why this one's my favorite in the real world. So the story, as you'll see, I'll read it to you, but is one about a black hole that kind of swallows up the universe. But there is a secret story that goes in reverse if you have one of these, a UV torch, and you shine it on the page. Okay. And you can see, can you see? Let me see there. Where's some words? There they are. So it's really hard to see because I have bright lights.
And I think your green screen is mucking up. And I do apologize for those who are listening via Apple, Spotify, or Google. Yeah. This is a bit of a visual thing, but I'm sure Chris will do a fantastic job anyway.
Yeah, I can explain what happens. So there is a special ink that's printed on the page, which is completely invisible. and then fluoresces under ultraviolet light. So there's lots of like little elements and a full story that goes in reverse. So for the people watching on YouTube, they can see the story on the screen, but for those listening, they can hear the story. All right, so here we go. But the book is called "There Was a Black Hole That Swallowed the Universe," and the pictures are by an illustrator by the name of Susan Batory. And it goes like this. There was a black hole that swallowed the universe. I don't know why it swallowed the universe. Oh well, it couldn't get worse. There was a black hole that swallowed a galaxy. It left quite a cavity after swallowing a galaxy. It swallowed the galaxies that filled the universe. I don't know why it swallowed the universe. Oh well, it couldn't get worse. There was a black hole that swallowed a star. It couldn't get far, that bright shining star. It swallowed the stars that lit up the galaxies. It swallowed the galaxies that filled the universe. I don't know why it swallowed the universe. Oh well, it couldn't get worse. There was a black hole that swallowed a planet. Very organic, this fine-looking planet. It swallowed the planets that orbited stars. It swallowed the stars that lit up the galaxies. It swallowed the galaxies that filled the universe. I don't know why it swallowed the universe. Oh well, it couldn't get worse. There was a black hole that swallowed a cell. It might get unwell after swallowing a cell. It swallowed the cells that gave life to the planets. It swallowed the planets that orbited stars. It swallowed the stars that lit up the galaxies. It swallowed the galaxies that filled the universe. I don't know why it swallowed the universe. Oh well, it couldn't get worse. There was a black hole that swallowed a molecule. It thought it was fuel, a big molecule. It swallowed the molecules that fed the cells. It swallowed the cells that gave life to the planets. It swallowed the planets that orbited stars. It swallowed the stars that lit up the galaxies. It swallowed the galaxies that filled the universe. I don't know why it swallowed the universe. Oh well, it couldn't get worse. There was a black hole that swallowed an atom. It's hard to get at them, those tiny atoms. It swallowed the atoms that built up the molecules. It swallowed the molecules that fed the cells. It swallowed the cells that gave life to the planets. It swallowed the planets that orbited stars. It swallowed the stars that lit up the galaxies. It swallowed the galaxies that filled the universe. I don't know why it swallowed the universe. Oh well, it couldn't get worse. There was a black hole that swallowed a neutron. A good start to build on, a neutral neutron. It swallowed the neutrons that stabled the atoms. It swallowed the atoms that built up the molecules. It swallowed the molecules that fed the cells. It swallowed the cells that gave life to the planets. It swallowed the planets that orbited stars. It swallowed the stars that lit up the galaxies. It swallowed the galaxies that filled the universe. I don't know why it swallowed the universe. Oh well, it couldn't get worse. There was a black hole that swallowed a quark. That's all there was, and now it's dark.
Love it.
Yeah. Yeah. So it's a fun little story. I don't know if you recognize the cadence to that.
Yes, it was very nice. Excellent, excellent. And of course, you're going just beyond physics as well. You've got chemistry, as I mentioned earlier. You've got evolutionary biology mentioned. What other interesting topics can we expect to see?
So we have technology topics like neural networks and blockchain, and we have some more pressing topics lately. So there's pandemics for babies and climate change for babies as well.
Obviously available at all good bookstores.
Yes, of course. So yeah, visit your local bookstore. Yeah, great to support your local bookstore. I think many major cities, certainly around the world, definitely in Australia, will have even children's bookstores, which are great places to support.
Now, is this a possible future of moving away from academic research and going into global J.K. Rowling style?
Well, yeah. So many of the books there, they kind of mirror my academic drawings, the ones I illustrate, and it was, with foresight, what I should have done was created characters, right? Yeah, you need characters for the Netflix special. Yeah. So I don't think I would quit academic research. I love it too much.
That's a nice side little thing on the side. I mean, and I guess what it draws out again I've noticed with a number of interviewees is that you've got this analytical side, this that's really your bread and butter, but there is also a very strong creative side as well. And I've found that so many of the people I've talked to so far have almost a complete alter ego. This is like this strong physics side, but they're incredibly creative, whether it's in music or cooking or, in your case, storytelling with kids' books. It's a great creative outlet, I guess, for you.
It does, and they feed off of each other too, I think. You certainly need a lot of creativity to solve challenging problems, even if they seem very abstract and analytical. And the other side helps too, because, artistic endeavors, they're not just completely random things, right? Like there's it's like a balance, right? You have to follow the rules, but break them slightly, right? So yeah, I couldn't just have a book with just gobbledygook and no sentences, right? So there is a set of rules that you have to follow, and having that analytical mindset and training allows you to kind of see those rules and then know where you should bend them. So it's quite formulaic in a sense. Yeah.
Well, it's been great talking to you, Chris. I don't have little kids to sell those books to, but I'm sure there are lots of people hopefully listening who may have little kids or will have little kids, even as gifts. And they're doing pretty well too, aren't they?
They are, yeah. We got a few million sold worldwide.
Wow, that's impressive, very impressive.
So there's going to be, I'm worried that, in 15 years, there's the cohort of quantum physics students coming in. It's going to be maybe a bit too much for the university to handle.
That's not a bad thing at all.
Yeah.
Well, thanks again, Chris, and hopefully an opportunity to speak at another stage. And yes, check out Amazon, check out Booktopia, check out any of the quantum physics for books, and certainly just look up Chris Ferrie on his website, and you'll find where you can get any of his books. Thanks again, and take care.
Thanks, Paul. Bye.
Well, I hope you enjoyed this episode. Please subscribe to get notifications of up-and-coming interviews, as well as my other physics content. My name is Paul from PhysicsHigh. Till next time.